thymine appears only in DNA, and uracil appears only in RNA, and they differ by a methyl group. You see uracil is a hydrogen here, whereas thymine is a methyl. And I know that cytosine and guanine form a base pair in both RNA and DNA through hydrogen bonding, and likewise adenine and thymine in DNA. There you go. So likewise, adenine and thymine make base pairs through hydrogen bonding. That's in DNA, or adenine and uracil in RNA. This stuff you had in high school biology, I'm quite confident. So stuff like that I think is reasonable to know. But you guys in chat should be able to see it now. I have the class notes are the thing that I'm sharing now. And I just want to keep these around in case we need these structures as we go on. But stuff like that is fine, but you know, lengthy essay questions and exactly how translation and transcription work, no, I don't think that's appropriate for our class. And you'll get those in your upper level classes, not to mention that you've probably already had them in freshman level biology. Good, so, but we've gone over these structures, and as I said, I certainly don't expect you to memorize these structures. Like I said, if you understand that there are these things called purines and these things called pyrimidines, and they're called that because there are actual compounds called purine and pyrimidine, and so these nitrogen bases kind of look like those two heterocycles, and so that's why they're named that way. I think I gave you the silly mnemonic device that I use to remember which are purines and which are pyrimidines. I like to remember that pyrimidine is the bigger word, but it goes with the smaller heterocycle. And purine is the smaller word, but it goes with the bigger heterocycle. So the size of the heterocycle and the size of the name does not go together. That's how I remember. I have no doubt that a lot of you can come up with an even better way to remember that. But if that's helpful to you, you may feel free to use that. So basic things like that I think are fine, and I think are worth knowing. But my main goal with chapter 18 is that you come out of it with a structural understanding of how DNA and RNA are put together, up to and including the point of maybe being able to draw a small oligonucleotide, 2 or 3 bases. And that I think will be more than enough. I certainly am not going to go into heavy-duty molecular biology, nor expect that of you guys. But as I said, if you want to know what it is you will and will not have to know, I've put it in the syllabus. And I think I've also put it in the class notes here. Certainly focus on what we go over in class. As for the OWL, I really need to double check that. There may not even be a chapter 18 assignment. I will double check. If there is one, I'm fairly certain it won't be graded, but I will double check that over the weekend. Anyway, on that note, I should announce, if I have it wrong, so our exam is a week from today. That means that on Monday and Wednesday, that's the 5th and the 7th, we'll cover chapter 15, which is on lipids. We'll do another biochem chapter. And as you can see in the syllabus, that material will not be on Friday's exam. That'll be in exam number 3. Why did I do that? I think that what was on my mind at the time, though I don't completely remember, is I just didn't really want to put the exam on Wednesday. I mean, sometimes I do that, sometimes it can't be avoided. I kind of like, when I teach Monday, Wednesday, Friday, I kind of like putting it on Monday, because then you have the weekend to study, or Friday, because then at least you get it over with and can do other things on the weekend. So for assurance, what assignments are due tonight? There should be some that are due tonight, but I will have to double check that. Well, let me see. What about the chapter 11 assignments on amines? Yeah, that I would expect would be due tonight. 18 I will have to double check on, but as I said, there might not even be an OWL assignment. And if there is, I'm fairly certain it will not be graded. So it might be that next week is 18 and 15, and there will be, basically after this weekend, if you continue to see nothing for chapter 18, oh, it's not graded, okay. There might be a few questions there that are not graded. And I wouldn't be shocked if it's the same for 15. These biochem chapters, they give me very, very few questions. And often of the few that they give me, I can't even use them because they focus on molecular biology. So we'll see how it goes. But study guide for exam 2, yes, I will put that up this weekend. It will include some questions from last semester's exam 2. The chapters that are on the exam are listed in the syllabus. I'll read it off for you right now from the syllabus. Exam 2, 4, 5, 11, 18 is what's on the exam. And it sounds like it's 4 chapters, but really 11 and 18 are almost like half chapters because we skipped so much in that chapter. I couldn't hear in the beginning, how do we get the extra points? I think someone was just joking around. There's no extra points. Sorry, but I think they were just joking. Certainly I wasn't talking about anything involving extra points. I'd better just be as clear as I know how to. There is no way to get extra points. There, now I've said it. Now at least it isn't flying around on the internet and what have you. Okay, so we've gone over these nitrogen bases. Let's see how we can put them together to make a nucleoside, and what on earth is a nucleoside. And then we'll also go over how a nucleoside differs from a nucleotide. So, I defined a nucleoside in the class notes. It is an NO-acetal, and we will define what that means visually. We'll define it by the structure. But it's the NO-acetal of a nitrogen base, any of the 5 structures. Why is what ruined? Oh, I'm just gonna have to let people talk. Next exam will go much like the previous, and that's the end of that. Okay, so basically what we're gonna do to form a nucleoside is we're going to combine one of those nitrogen bases, which again, I don't expect you to memorize those structures. I don't have them memorized either. If you need any of them for the exam, I'll give them to you, either as part of the question or on a separate page, something like that. But we're going to combine those structures you may even recall from your high school biology that DNA and RNA consist of base plus sugar plus phosphate backbone. And the base and the sugar by themselves are what we're going to call a nucleoside. And it's only when we start adding the phosphates that you change the S to a T and you get a nucleotide. So the sugars that we're going to combine, I'm getting myself confused. The sugar that we're going to combine our, wow, it's been so long. The sugar that we're going to combine our nitrogen base with is going to be either ribose or 2-deoxyribose. And let me draw them for you now. Again, I don't really care if you memorize them. I've obviously done a pretty poor job at memorizing them myself, but I think I remember now. It's just been a while. CH2OH over here. And then, actually, this OH here can go either up or down. And by the way, you'll notice this rather peculiar way of drawing structures, where I'm using these straight lines to show one bond going up, one bond going down. These happen to be called Hayworth projections, H-A-W-O-R-T-H. I don't know that I really care if you memorize that name. There are pluses and minuses to Hayworth projections, but biochemists use them a lot. The thing that's good about them is it becomes very clear whether a group is pointing up or down. The bad part is the bond angles are all screwed up, right? We need 109.5 degrees bond angles for sp3 hybridized atoms, which all of these are. All of the carbons and oxygens are. So this molecule is ribose, at least as you will find it in RNA. And there's also 2-deoxyribose, which basically just is a CH2 over here. Instead of having an OH there. So OH, you do not need to memorize these structures. But I certainly will expect you to know the difference between the ribose and the deoxyribose. If I think there are any of these structures in this chapter that you will absolutely need in order to answer a question, then I will give them to you. And OH over here. I should have drawn these a little bigger. It's a little crowded. But be that as it may, this is 2-deoxyribose. And I'll show you where the 2 comes from in just a second. I mean, I guess I have ribose and deoxyribose memorized. Those aren't too hard. The nitrogen bases I give up. I will never even try to memorize those. But the reason we call it 2-deoxyribose is because carbon 2 is this one over here. Carbon 1 is this one. And that's just how it's been defined for years and years. Carbon 1 is what's called the anomeric carbon, and it goes by a couple other names too. And we'll learn why it's called that when we get to sugars. We will do a chapter in carbohydrates as well. We find 2-deoxyribose in DNA, and that's where the D in DNA comes from. It's because the sugar, the ribose, in DNA is deoxygenated. You see how we go from having an OH pointing down to just a CH2 over here. So, like I said, I don't know that I expect you to memorize these, but these are structures that we can understand. We can see a cyclic ether over here, and sugars indeed can form structures with cyclic ethers, simple monosaccharides like ribose, like glucose is another. We'll learn about glucose when we get to the chapter in carbohydrates. And this carbon over here, the one we've called carbon 1, that carbon is part of a functional group that's known as an acetal. We'll learn more about that functional group and define it in later chapters. But for now, I think you can see that this carbon is between 2 oxygens, has 2 single bonds to oxygen. And that's what makes it an acetal. So for now, I think that picture, this structure, is a good enough definition. So in order to go from a nitrogen base to a nucleoside, we're going to combine one of these 2 sugars with one of the nitrogen bases we talked about. So let me open up, you can refer to your class notes. I'm looking at the first page of your class notes. I'm going to take adenine, just because I feel like it, and combine it with ribose. And we're going to get the structure of an adenine containing nucleoside as we would find it in RNA. And the main difference here is instead of OH over here in carbon 1, we're going to attach it to, what is the definition of what? The definition of nucleoside I'm going to define in a picture rather than in words. We're just going to do an example over here. Adenine. Just let me get the structure in. I'm just copying this straight from your class notes. I certainly don't have this guy memorized, nor would I ever expect you to. Double bond N. I think I have a double bond here too. Yep. And then double bond to the carbon, and that carbon bonded to the nitrogen. Did I miss anything? Nope. And we've got all these nice lone pairs and all these nitrogens. This one over here as well. Okay, so let me just, now that I've got my nitrogen base in and can think a little more clearly, this is going to be a nucleoside, and the definition will be based on the picture. A nucleoside containing adenine whoa. And it will be of the type that we find in RNA, and that will be clear once I finish drawing it. Of the type found in RNA. That's what I'm trying to draw here. And so I'm assuming you see a question that looks something like this: draw this. Well, since it's going to be of the type that we find in RNA, that means that carbon 2 over here is not going to be deoxy. So it will have the OH in carbon 2. And we'll still, of course, have the OH over here in carbon 3. Or really, I almost should say 3 prime. More on that in a second. And then CH2OH. So what makes this a nucleoside, the way you know it's a nucleoside when you look at it, is because I see one of the nitrogen bases over here attached by a nitrogen to the sugar. Everyone see how this structure is the same as this structure. They both are ribose molecules. That's one thing to focus on. But instead of having just an OH attached here, I replaced that with one of the nitrogen bases. And that's what makes it a nucleoside. So the definition of a nucleoside is something like this. It's either ribose or 2-deoxyribose connected to a nitrogen base by one of the nitrogens. And it's always going to be this nitrogen. They call that nitrogen 9 because of how they number these things, which I don't even know how they do it. That was decided, I'm quite sure, over 100 years ago. And if you wanted to find out why it's numbered the way it is, you'd need to go look it up in Beilstein, which I hope your German is good, because they're only available in German. But anyway, that was decided a long time ago. This structure I simply copied from your class notes. And if you needed that structure for something on the exam, I would give it to you. I don't expect you to memorize that. This structure I more or less copied from up here. Let's just make sure we're clear on that. Can everyone see that this part of the molecule with the sugar is the same as this molecule up here? Is everyone clear on that? The only difference is we've changed the OH to a nitrogen base. And that gets us what you call a nucleoside. And this would be of the type that we find in RNA. We can tell that because of the OH on carbon 2. If it were a DNA type nucleoside, then this OH would be an H. So that's the only difference there. Except again, we need to remember, we use thymine in DNA and uracil in RNA. Those two molecules are given in your class notes. I don't expect you to memorize them. But if you take a look at them, you'll see that they only differ by a methyl group. So my point being, yes, this is a big molecule, but already we can make some sense of it. And we can break it down into its component parts so that it's not as scary as it was before. All we're going to do is take one of the nitrogen bases and replace the OH and carbon 1 of the ribose or deoxyribose. And so let's number these carbons. You'll actually often see them with primes. So they'll talk about the 1' carbon. This will be 2' over here. 3'. The 4' carbon is over here, and the 5' carbon is the CH2 of the CH2OH. And why do they use those primes? This now, again, and not trying to put them down, but this is the sort of thing that your biology and biochem professors will never tell you. But I always wondered it. Why do we get primes all of a sudden? What's going on? Well, the reason we use primes for numbering the 5 carbons in the sugar is because numbering without primes is for the atoms in the nitrogen base. And which, by the way, I don't expect you to memorize this, but it turns out that in adenine and I think guanine, it's this nitrogen which happens to be nitrogen 9. I couldn't tell you what atoms 1 or 8 are in this ring system. But that's why they do it. When they use numbers without primes, they're referring to atoms in the structure of the nitrogen base. But when they go down to the sugar, they use primes. And that's going to become important when we get to the 3' and 5' carbons. That may ring a bell from your biology class. They talk about the 3' end and the 5' end. So that is meaning, but the primes come because we're considering atoms just in the sugar, just in the ribose. I'll do another example. What might a nucleoside look like if it were in DNA? Let's maybe I'll even just draw in my sugar first. Well, first of all, DNA type nucleosides stick out because carbon 2 or 2' over here is just a CH2. There's no OH there. The rest will look much the same. OH pointing down over here. And then our 5' carbon up here. CH2OH. I am recording, yes, thank goodness. And over here, I'll put one of the nitrogen bases. Maybe I'll even put thymine, since thymine is found in DNA. So it makes sense to put it here, as opposed to uracil. Now, could you get your hands on the compound with the uracil here instead of a thymine? Sure, of course you could, but it wouldn't occur naturally. That's not a natural combination. In real DNA found in real living creatures, you would only have thymine here. Double bond here, right? Nope, I lied. Oh, right, because that nitrogen already is 3 bonds. So we got a lone pair here, a lone pair here. Of course, lone pairs in all the oxygens. So this now is a nucleoside containing thymine. I think they would even call it thymidine, meaning a nucleotide containing thymine of the type that you would find in DNA. So if you want to copy the wording from over here, that would also be fine. This is a nucleoside containing thymine. Let me even not do thymidine because I don't want to be confusing. This is a nucleoside that contains thymine of the type that you would find in DNA. And, you know, don't get married to that wording. I just am trying to phrase it as clearly and simply as I can. But Al will give you some ideas, insofar as it's not graded, of other ways of phrasing that. And yes, I will put up a study guide for each exam within about a week of it being taken. I'm planning to put up yours today sometime for the second exam. It will list all the topics that we've covered, which I basically just took right out of your textbook. And I will also put some sample questions from last year's exam with answers. Good, so, but the main difference here, because it's the DNA type, again, always look at that 2' carbon, this one over here. And so you'll find that you have a hydrogen pointing down over here, if it's of the type that you'd find in DNA. If it's RNA type, then you'll have an OH over here. And that's the only structural difference in the sugar between the two. Good, and again, my main point here is not whether you can memorize these big structures. I don't think I care very much if you can at all. And you can see that I, at the very least, have not memorized the nitrogen bases. I just have never found that something to be worth my time. But even so, we can understand these structures. We're just going to replace the OH of the sugar by itself with one of these nitrogen bases. And it's always going to be this nitrogen in the 5-membered ring. That will be for adenine and guanine. And it's this nitrogen here at the bottom of the ring in cytosine, thymine, and uracil. We'll just take away the H attached to that nitrogen so we can form a bond to carbon. And that is the definition of the term we used earlier, which is in your class notes, of the so-called NO acetal. N and O in this case mean literally nitrogen and oxygen. And so this here, what you see here, that's the definition of an NO acetal. I'm using a structure to define it rather than words. And whenever you see another one over here, a carbon between a nitrogen and an oxygen, you'll always see that in nucleic acids, whether nucleosides or nucleotides. There are no exceptions. You'll always see that. And with that, we've done most of the heavy lifting for understanding the structure of nucleic acids. Mostly what I want to do today is contrast a nucleotide to a nucleoside. It's going to be fairly easy to get one. I'll just tell you right now. In order to turn a nucleoside into a nucleotide, we'll simply add either monophosphate or diphosphate or triphosphate, and I'll write down and define those for you guys, on either the 5' OH or the 3' OH. In other words, you'll replace the H with either monophosphate, diphosphate, or triphosphate, and presto, you've got yourself a nucleotide. Simple as that. And that also tells us something about how to put multiple nucleotides together. So from this, you can understand the primary structure of both DNA and RNA. And that's really all I'm hoping to do today. If we get that far by quarter of, I'll be very happy. I don't really care if you memorize all the other stuff in the chapter, all of that molecular biology stuff, which again, I'm not putting it down. There's nothing wrong with it. I just don't think it's appropriate for a chemistry class. We're going to focus on the structure, just like we always do. You'll have noticed by now that we organic chemists are rather obsessed with structure. So that's all we're going to focus on. Good. Any other questions on these structures? Other than what's going to be on the test. That's really the only question there is, isn't there? Well, again, I'm not going to ask you directly to draw these, nor am I going to directly grade your structure drawing ability. But I think I've gone over these with a fairly basic and straightforward structural understanding of how we put the pieces together in order to make the larger ones, in order to go from nitrogen bases to nucleosides. We've learned about the sugars that we use, which are going to be ribose and deoxyribose in RNA and DNA respectively. And this gives you an idea of how the nitrogen base is connected to that sugar molecule in order to form a nucleoside. So what would be a question? Well, let's make up a multiple choice question. Which of the following is a correct structure of a nucleoside of the type you would find in DNA? Would be completely reasonable. But I don't promise that question will be on it, nor am I going to give every last hint away. But something like that would be reasonable. Something that would be a multiple choice question. Because like I said, I'm not going to be grading your structure drawing directly. It will still be all multiple choice. So with that, actually, I don't really want to erase everything. Let me keep my adenine one over here and recycle that. And from that, we're going to get to our understanding of the difference between a nucleoside and a nucleotide. So DNA is an H in carbon 2 and RNA is an OH in the same place. Exactly. And that's exactly the level of understanding that I'm expecting of you guys. We want to look at these from the perspective of a chemist. What is their structure? And you're exactly right. I couldn't have said that any better myself. And again, my point is, as scary and big as these molecules seem to be, well, I don't want you to underestimate the material, but as scary and big as these molecules seem to be, we can make sense of them already, even at this level, not even half a semester through an organic chemistry class. Good. So here then is our nucleoside. Happens to include adenine, though like I said, I don't care if you memorize that structure. You've already noticed, I don't have it memorized. And we can tell, just as Francis said, that there's an OH in the 2' carbon, so that means this is of the type we'd find in RNA. If it were DNA type, this would just be a hydrogen, not OH. So then, what is the difference between a nucleoside and a nucleotide? Well, just like we got a nucleoside by putting together the ribose sugar with the nitrogen base, we're going to convert a nucleoside to a nucleotide by adding on some kind of phosphate group. And in your biology and biochem textbooks, they will often get very sloppy and just put a P in a circle for a phosphate. You might have seen something like that already. And that's fine for those purposes. However, that's not going to work for us. There's basically 3 types of phosphate groups: monophosphate, diphosphate, and triphosphate. And monophosphate would look like this: minus, minus. Something like that. Give or take one of these O minuses being actually OH. Doesn't really matter. That depends mainly on pH. That's not going to be a huge deal for me either way. In Gen Chem, you would have written this as PO4 minus, the phosphate ion. So this is a monophosphate. Actually, I just realized something. one of those oxygens is going to get connected to a carbon. So we don't really want to draw a minus charge. We really want to draw a bond over here. And that bond is going to be connected to a carbon. And then similarly, we also have triphosphate. The only difference is the diphosphate will be like, kind of like two of these things put together. O minus over here. Double bond O up here. And again, notice that our phosphorus atom is hypervalent. It's got, what, 2, 4, 6, 8, 10 electrons around it. And that's allowed. You can do that with phosphorus. Nitrogen, never. But phosphorus, it's possible. Phosphorus can also obey the octet rule. You'll get a molecule that's similar to an amine, except with a phosphorus instead of a nitrogen. We call those molecules phosphines. Wasn't phosphine in the news just recently in the planet Venus? They found some in the atmosphere, upper atmosphere of Venus, and are saying the molecule is generally comes from life processes, and so they're all excited. And I have no comment either way on that, though it does sound very exciting. But in phosphines, the phosphorus is not hypervalent. That has 8 electrons around it, just like the nitrogens and amines. This phosphorus is hypervalent, so this will be your diphosphate ion. And I think you can already guess what a triphosphate group looks like. But we'll draw it out anyway, just to be thorough. So a triphosphate will, completely unsurprisingly, have 3 phosphorus atoms alternating with oxygens. And this will be a triphosphate group. One place you'll have heard of the triphosphate showing up is your ATP. Ring a bell? Adenosine triphosphate. And we could actually draw adenosine triphosphate. In fact, I think we might be about to be, whether we want to or not. So this oxygen is going to get connected to a carbon, O minus over here, and then we're done. And that's the triphosphate ion, or triphosphate group. And so all we're going to do is put any one of these 3 things in place of the hydrogen on the OH on either 3' or 5'. And then we will go from a nucleoside to a nucleotide. We'll put any one of these 3 groups on either the 3' oxygen or the 5' oxygen. And then you've got yourself a single nucleotide. So here's a nucleoside. And then am I going to have to copy all that again? Yes, I guess I am. Well, I'm sure getting a workout with my mouse skills. And I have to be entirely honest. I don't know if, actually, I'm not going to commit to this being ATP. I don't think it is. Because I think ATP is DATP, so it's going to have an H over here. It's going to be DNA type, not RNA type. But I will make this into a nucleoside by adding by adding one of those 3 phosphate groups. And that's really the main thing I'm expecting you guys to get out of this. Is first of all, what's the difference between a nitrogen base and a nucleoside and a nucleotide? Because it's like I said, later on in your upper level classes, they are not going to explain that to you. They're just going to go, here's your nucleic acids, learn it, live it, love it. But I think with some basic understanding of structure of organic molecules, it's manageable. You can make some sense out of it. And I forgot a nitrogen here, didn't I? There we go. Good. So instead of OH, I'm going to put one of these other groups on. I could put either monophosphate or diphosphate or triphosphate. I think I'll put on a monophosphate because I'm getting tired already. But whether I put mono or di or triphosphate on either the 5' or the 3' oxygen, then you'll have yourself, this is a nucleoside, this is going to be a nucleotide. And that one little subtle change is all the difference. Good. So that's all there is to it. And I think understanding those subtle differences between what makes it go from a nitrogen base to being a nucleoside, and what's the difference between a nucleoside and a nucleotide, I think that's going to be helpful to a lot of you, maybe not every single one of you, but to a lot of you going forward. Because again, that's exactly the sort of thing they won't mention, except maybe in 3 seconds in a biology class. But as you see, it's something that we can make some sense of. So that leaves us with 11 minutes left. I have just one last thing to cover, which is how do you connect multiple nucleotides together so you get your strand of DNA or RNA? And we'll, we understand it's actually a double strand, right? It's 2 single strands connected by hydrogen bonds down the proverbial rungs of the ladder. But that is also something that's not hard to understand. And I'm reading, it's right in, I'm reading right off your class notes. Polynucleotides and nucleic acids formed by connecting the 3' OH of one nucleotide to the 5' OH of the next via a monophosphate ester. And with what we've treated with our treatment so far, that's something we can understand. And I'll basically end today with that. And then if I can make it through that without face planting, I'll say, thank God I at least made it through one class without something horrible happening. Good, so let's actually pick one. I don't have really a sample question here. Let's draw the, let's have some fun. Let's draw the dinucleotide Cu. So it's going to have a cytosine and a uracil, which by the way already tells us we'd better make our sugars RNA type, because uracil is only found in RNA. So, so let's say we were asked that question. Draw a Cu dinucleotide. Well, what I would do is I would start with the OH and the 5' carbon of the cytosine nucleotide, hydrogen on that same carbon down here, and I'll put my 5-membered ring over here. What is the name of the last one we drew? I don't remember. I think it was the same nucleoside we drew, except I put a phosphate, a monophosphate on the 3', no, I'm sorry, in the 5' carbon. But I don't think it had a name really. It was just a single nucleotide. And I'm going to put my cytosine here, which again, I don't expect you to memorize this structure. I'm copying it off your class notes. That's going to be pretty awful unless I fix it. And H2 going up here. And then double bond to nitrogen over here. And then carbonyl in between these two guys. So there's my cytosine. And since it's RNA, which I know because it uses uracil, that means I'd better put an OH over here. And then what makes it a dinucleotide, that connection goes from the 3' oxygen of this sugar to the 5' oxygen of the next sugar. And in between, we will put a monophosphate using the same definition we had on the previous page, or whatever the page was that I drew the phosphate esters on. Whoops. And that, by the way, is invariant. There's always a monophosphate in between. This is the 3' oxygen of this first sugar, and this is going to turn out to be the 5' oxygen of the next one. That's always the case. There are never any exceptions. It's never a di or a triphosphate. And then here's my next sugar molecule. I'll drop in my 5-membered ring. This again will have, as someone pointed out earlier, the OH pointing down in the 2' carbon, because this is an RNA type of nucleotide, dinucleotide. And then this will be OH, hydrogen here, and I said I'd put uracil here. Where's my uracil? There's my uracil. Again, I'm just copying this off of your class notes. We'll just take the hydrogen off the nitrogen and instead make a bond between the nitrogen and the carbon over there. So double bond over here. And NH over here. And then carbonyl in between the two. And presto, we've got ourselves a nucleotide of a dinucleotide. In this case, this dinucleotide, Cu, but this would be of the type that you would find in RNA. And if you zoomed down to the molecular level and found a single strand of RNA with cytosine followed by a uracil, this is what you would see. And it will always have this monophosphate ester in between. That's invariant. So, but I think you can see this falls into the definition of nucleotides that we gave. We said you just want to put a mono or di or triphosphate on the 3' or 5' OH, and then you've turned a nucleoside into a nucleotide. But to make a dinucleotide, you just put a monophosphate, and it's always a monophosphate, in between the 3' oxygen of the first one and the 5' of the second one. If we wanted to add a third one, if we wanted to draw a trinucleotide, same procedure. We'd take this oxygen, and instead of the hydrogen, we'd use another monophosphate ester looking exactly like this, and that would then, I'll even show you. Let's pretend, I won't go all the way, but let's pretend that we wanted to draw a trinucleotide. Well, same thing. I can just copy that straight down here. We'll have our monophosphate ester over here. And then this oxygen will be the 5' oxygen of the next sugar. Right, and it would go on like this. And then we'd have another 5-membered ring for our sugar over here. There'd be another nitrogen base over here, and on and on and on. That's what the primary structure of, in this case, RNA looks like. And if it were DNA, as a student pointed out earlier, then this OH, these OHs on the 2' carbon would just be hydrogens. That carbon just becomes a CH2. So again, yes, these are extremely large and somewhat complicated structures. But when you break it down into their pieces like this, I think it's not nearly as bad as it might at first seem. And I think that now that we know something about amines from chapter 11, I think these are some compounds that we can understand. And like I said, I really don't care if you memorize any of these. I mean, I guess if you had to memorize something, if you wanted to memorize ribose, that'd be really great. That'd make your life easier, I think. If you know ribose, then you know 2'-deoxyribose. That gets thrown in for free. I certainly don't care if you know the nitrogen bases. I think I've said that repeatedly. Mono, di, and triphosphate are pretty self-explanatory. But my main goal here is that you understand how all these pieces are put together and how to differentiate a nitrogen base by itself from a nucleoside from a nucleotide. And if you can do that, I'm pretty happy. I certainly don't care if you memorize much beyond that. And certainly we will leave off all of the molecular biology. I don't think that's appropriate for our class. And with that, I can't really think of anything else. With that, we're ready to go into chapter 15, which is on lipids, and again, will not be on Friday's exam. I will try to get up that study guide for you guys today. The main idea of this page is what is a polynucleotide, in this case a dinucleotide. How do you make them? And this shows you that you make a dinucleotide by putting a monophosphate ester in between the 3' oxygen of one nucleotide and the 5' oxygen of the other. That, I would say, is the main idea of this page. Something like that. Other questions then? Question for exam 2 is exam cumulative? Well, I'm certainly going to focus on the chapters since the previous, but you're going to see some things that were also on the previous exam. It can't be helped. The material is cumulative by its very nature. In other words, you don't get to say, oh, this question asks about molecular weight. That was in chapter 1. That's not on the, you don't get to say that really in chemistry. But certainly I'm going to focus on these new chapters, which are what, 4, 5, 11, 18. Certainly. But you're still going to need to know all the terms. You know, you still have to know your functional groups, for instance. So yes, this course is cumulative, but I'm certainly going to focus on the exam since the previous exam. Sorry, the chapters since the previous exam. Good, well, I'm not ashamed to let you guys go a minute early. 10 minutes I'd be a little ashamed, 1 minute not so much. So I will try to get that study guide up for you today. And other than that, have a great weekend. We'll see you Monday.